And hello, everyone. On behalf of my colleagues, welcome to this month's talk from the Johns Hopkins Institute for Assured Autonomy seminar series, co-sponsored by the Computer Science Department of the Whiting School of Engineering. Each month, we will have a talk on research topics at the intersection of assurance and autonomy. This seminar will be recorded. Introducing our speaker today is the IAA's co-director, Tony DeBurra. Tony, take it away.
Thank you, Ken, and hello, everyone. It's my pleasure this morning to introduce Gregory Falco. Greg is an assistant research professor at Johns Hopkins University at the Institute for Assured Autonomy and the Department of Civil and Systems Engineering, where he will be an assistant professor beginning in the fall. And by the way, IAA's first faculty hire with a part-time role at APL. Greg currently serves as an NSF Fulbright Scholar in critical infrastructure cybersecurity in Iceland. His research is at the nexus of AI and cybersecurity as he develops new technology for the safe and secure operations of cyber-physical systems. Greg is also a postdoctoral scholar at Stanford University, a research affiliate at the Massachusetts Institute of Technology, and a cyber research fellow at Harvard's Belfer Center. Greg's research has been pivotal in the development of national space policy and is widely deployed in industry. Previously, Greg was an executive at Accenture, where he co-founded their Smart City division. His work has been featured in documentaries with the BBC, interviews with NPR, and other domestic and international media outlets. He is internationally recognized as an inventor and thought leader, having been listed in Forbes 30 Under 30 for enterprise technology. Greg holds a BS from Cornell University, an MS from Columbia University, and a PhD from MIT. Greg, it's all yours.
Hey, thanks very much, Tony. Can everyone hear me okay? I guess that was the point of the sound check earlier.
Sounds good.
Great. Thanks, everyone, for joining. I know that there are a lot of competing priorities these days with Zoom. So thanks for taking the time out of your day to kind of listen to us for a few minutes, even if it's just for a few minutes. So today I'm going to be talking about human-centered autonomy for resilient space systems. And this talk is, I would say, wide-ranging, and also I look for your feedback because I don't think I'm going to give you a lot of answers today. I am looking to help define the space, and I would love everyone on the call's input for how do we continue to refine these questions that we need to look at relating to human-centered autonomy for space systems. And we're going to be talking about this a lot from the context of how do we look at systems that we've designed here on Earth that have levels of autonomy in them, varying levels of autonomy in them, and then how do we start applying that to a greenfield environment like space. So as Tony mentioned, currently I'm over here in Reykjavik, Iceland, as a NSF Fulbright Scholar in critical infrastructure cybersecurity. And this is an interesting place to be right now because they are actually building out a space program in the country, and they are building it from scratch with very little resources. And they have interests and their sights set on being a world definer in how autonomous systems will dictate the future of spaceflight. And the questions about how are they going to be able to do this, and where are they going to get the resources? Those are very real questions that they haven't figured out yet. But what's interesting is that they're trying to, again, tackle this problem, the space problem, from a greenfield perspective. They have no infrastructure. They don't have a lot of research that's defined the space, but they've set a vision for themselves to kind of help define what this looks like. And so it's actually quite interesting because today what we're going to talk a lot about is how space operations and space systems offer this clean slate design opportunity for us as engineers to begin thinking about how do we build systems the right way from the ground up. And I think it offers the opportunity for countries and people who are maybe more used to not being part of these conversations to kind of jump in and say, hey, we want to have a defining role in this space because we don't have to have that legacy baggage of all of the old infrastructure that we are kind of trying to now upgrade and rely on for these new problems. So just a different perspective that I'm being exposed to here. And just to give you a bit of information about me, as Tony mentioned, I have a couple of hats currently. I'm currently a postdoc at Stanford. I also joint with MIT My work there is at Stanford is on more cyber policy and looking at things from an insurance standpoint. And many people don't think about insurance as a big player when it comes to assurance or from a cybersecurity standpoint, but it's increasingly important, especially in the US landscape, because companies and organizations alike are not really doing a great job necessarily at securing all their infrastructure. So they need the financial fallback of the insurer. And so insurance agencies and reinsurance companies are really trying to get their head wrapped around what are the risks of AI systems, and how do you actually begin defining and qualifying if a company that is using an AI system has a risk that is insurable. So these are some of the big questions that I'm looking at there. My doctoral work was at MIT. It was looking mostly at industrial control system security. And the reason why I started looking at space systems as a topic is because NASA's Jet Propulsion Laboratory funded a lot of my dissertation work. And they kind of saw that there was some great parallels, obviously, between the cyber-physical systems I was dealing with originally, which was in the energy space. And they were looking at how those had direct parallels to a lot of the cyber-physical systems in space systems. Had done some pre-doc work at Harvard, which was at the Belfer Center. Pre-doc is like the year or so after you finish your qualifying exams and have your get your dissertation done. Is a kind of a newish term, I guess. And the work I did there was much more policy oriented. And as Tony mentioned, some of my work was directly adopted in part for SPD5, which is Space Policy Directive 5 on critical cybersecurity principles for space systems. And so a lot of the work I had done there is now being engaged with as part of the National Security Council and Department of Homeland Security communities when it comes to space security. And had done some other work in other places before that. But possibly most important, what I'm going to talk to you a lot about today is how some of my industry experience kind of maps onto some of the current research that I'm doing in this space. And so before I did my doctoral work, I was at Accenture for nearly a decade, where I founded and led their smart cities business. And smart cities is all about taking IoT devices or industrial Internet of Things devices and kind of putting them in the built environment that help to control or sense critical infrastructure to improve the lives of people. And that's generally that marketing vision that we put out there. But there's a whole bunch of problems when it comes to actually doing this. And so starting this business at Accenture was very profitable for Accenture, but we create a lot more problems than we care to talk about sometimes. And so there's a lot of lessons learned from how do you actually design habitats, how do you design cities, places where technology needs to engage with humans. How do you design those from places here on Earth? And then how do we think about mapping some of those lessons learned into habitats that we are having still to think about and envision in space or on lunar habitats? In the process of kind of going through that mess at Accenture, I had a little bit of an epiphany at some point that there was a huge amount of liability and moral and ethical problems with kind of deploying IoT at scale for systems that were of critical importance. And then I bailed to go do my PhD work to work on that topic. And in the course of doing so, I had started a company on industrial control system security and had the opportunity to work extensively with NASA JPL and a number of other big tech companies in the US to try and deploy some security components around these increasingly automated systems. Many of them don't have AI behind it or have even notions of autonomy behind it, but there's a spectrum of autonomy. And I think that there's some definitely interesting implications of having seen that whole spectrum. And so today when I speak to you, I'm going to talk a lot about some of my experiences that I've had in industry and how those kind of should be relatable when we talk about what assured autonomy should look like when we design space systems. And finally, as Tony mentioned, I'm going to be, I don't know if you can have this little thing on my screen that shows me, and I don't want to see it anymore, sorry. So my current status at Johns Hopkins is their assistant research professor. I'll be joining full-time in the fall, and really excited to be working across the Institute for Assured Autonomy, as well as the Civil and Systems Engineering Department, and have my appointment at the Applied Physics Lab. So today, I'll tell you a little bit about the Artemis plan, and many of you on the call may have heard of this already, but essentially it was a plan that was created by NASA to create sustained human presence on the moon. And we have had ideas of going back to the moon as a country for quite some time. However, it doesn't always work out from a budgetary standpoint as we intend to. And so now this plan calls for, let's create this sustained presence and figure out how to design a habitat that would be associated with this. And when they talk about the Artemis plan, there are three main components that they've kind of articulated. NASA's articulated about what is part of the Artemis plan and part of the Artemis base camp. There is the lunar terrain vehicle, which is going to be an open air vehicle that will help. It's kind of like a moon buggy that will help astronauts get from point A to point B, maybe scientific research sites or other critical areas where they're going to be doing anything from science to figuring out how to deal with lunar regolith or some other nature of that sort. There's also going to be a habitable mobility platform, which is probably going to not be as versatile as the lunar terrain vehicle, which will be an open vehicle. But the habitable mobility platform is going to be a place that's kind of self-contained, and astronauts can live in there perhaps without their extensive space suits on. And then there's also going to be the foundational surface habitat, which is possibly where they'll be living and sleeping. But it's interesting because NASA has come out with some interesting material on this topic, but they haven't really fully defined how these components are going to work, or the different pieces of the puzzle, or the infrastructure that will support any of this base camp. And I think that's interesting because they're already starting to engage with companies and universities and researchers on how to actually begin doing some of this, but it's not quite public yet exactly all the details or any of the details of what's actually part of this plan. And so it gives us an opportunity as researchers to kind of think big about what they can be doing and kind of brainstorming publicly what is needed and what we should be thinking about. Another important part about the Artemis plan is that there's a heavy focus on driving international collaboration. And there are a number of countries right now that are signed up to kind of contribute different pieces of the puzzle for the Artemis plan. And so I'll talk a little bit more about the importance of that later. But the way I'm kind of seeing this interesting project evolve is they're really trying to do things that will define a future city or habitat on the moon. And that's a big undertaking from scratch, as everyone would already expect. So something that also I want to talk about a bit is the space is really hard. And this is a common trope of anyone talking about space from a technical standpoint or from any perspective. There's a whole bunch of hazards going on in space, and the moon is no exception. Everything from micrometeorites to radiation and other challenges, like we don't have any infrastructure there, so we have to go build everything from scratch. There's a lot of lunar dust on the moon that we would have to figure out how to deal with, and APL has actually been a big driving force in helping to start thinking through and figuring out these problems. So I think that one thing that we want to consider throughout this process as we talk through some of these plans and some of the challenges for human centricity, for the autonomy that is going to be required to deal with any of this, is that we're operating under abnormal conditions, even conditions that we would never think about here on Earth. And going back to the Artemis plan, one of the only main things that we know for sure and is called out throughout the plan is that there will be a series or many autonomous systems that would be operating the base. And we know that autonomous systems, we know that, as I said, there's a spectrum of autonomy for systems generally. And there's also a spectrum of the actual amount of AI or in terms of is it planning or is it machine learning? There's a whole bunch of there's a spectrum on that. But something that's important to note is that this base is supposed to be working with or without humans on it. There will be a sustained presence of operations on the moon, and sometimes people won't be there. So sometimes humans won't be directly in the loop on every operation. And so that's something important to consider as we envision the space habitat. So generally, getting pretty high level for a moment, when we think about reducing risk in extreme environments or any environments, there's kind of two hats that I like to bucket things in, and we can always argue about the very specific hats that actually exist from an academic standpoint, but usually when you try and manage risk or reduce risk, you're looking at things from a prevention standpoint or from a resilience standpoint. And again, there are officially like 7 or 8 different mechanisms to reduce risk. If you want to read about that, I published a paper in Science last year that talks about each of those, and it's kind of boring, so I'm not going to go into that. But the main buckets are really looking at prevention and resilience. And when we look at prevention for risk, well, again, I talked about some very basic risks when we said, space is hard, but prevention is actually tough to deal with when you have so many problems coming from so many different angles. You really can't always guarantee that you're going to fix or figure out and anticipate every risk that's going to come at you. So resilience ends up becoming a much more important issue. And that means resilience is being able to kind of get back on your feet once something comes at you. And so that's true from a machine standpoint, but also from a human standpoint. Making the challenge of driving human-centric autonomy even more difficult, because we're going to need to make sure as we design systems that would be operational on a lunar base, that not just the actual technology is resilient to external threats, and internal threats, but also that the humans that would work with those systems are equally resilient. And so, when we think about the nature of assuring these mission systems that are in space, there's a couple of different threat actors that we can be thinking about. There's, the threat actor of external attacker, which most likely more than not is going to be coming in the form of a cyber attack. Less likely that someone's going to be blowing us up with missiles on the moon immediately, at least. So looking at cyber attacks as a potential external threat actor from most likely nation states, perhaps in a smaller way, cybercrime syndicates. Then we're also looking at these natural hazards, which, as I mentioned earlier, anything from radiation to meteorites. And then we also have the idea of like self-inflicted problems when it comes to understanding the dynamics of the risks that we're under. So when I say self-inflicted issues, I'm talking about things like, did we design the technology correctly? Are there bugs in the code? Are the humans operating as they should be operating along with the technology? And so these are kind of how I'm describing a self-inflicting wound for looking at the challenges and the threats that we would have in space. And so these autonomous systems that we will have in space, the ones that are supposed to manage and deal with the lunar base for the Artemis plan, they're going to be exposed to these threat actors, and we need to start getting our head wrapped around what does that actually mean, and how do we make sure that this base can actually be sustained, and also make sure that the base is built for the right purposes. And so we need to start thinking about how we enable resilience of the systems that we have installed on the lunar base, so that we're able to know that we can survive all of the threat actors that are out there. And so this image here is of it's an artist mock-up, I think, of a servicing agent in space, where you might actually have a robotic arm that would help service another satellite or something of that nature. And so trying to think about that repair, that recovery, that's a big part of looking at resilience. And space, the operating environment of space, makes this all more difficult. So what do we need when we actually are designing this base? What ultimately will we need to have human presence? And so the Artemis plan does a little bit of articulation on this in a very basic way. They say we need energy systems, so probably in the form of solar panels. They need waste management systems. They probably won't have garbage trucks and stuff like that there, but they need a system to deal with this. They'll need communication channels. They'll need to be able to communicate back to astronauts. Will have to be communicating back to base, back to their own base, which might be on the lunar surface. They will have to be communicating back to the lunar gateway, which is going to be a habitat that is possibly orbiting the moon or in proximity, that is communicating in constant communications with the lunar base. And they also have to be communicating back to Earth. We'll also need a whole bunch of these autonomous systems running around. And when we say autonomous systems, most likely we're looking at some type of rovers, robots of the nature that you see in movies, but maybe more sciencey. And then also we'll need a way of manufacturing things. And that's something, these are all things that have been articulated as part of the Artemis plan. And to support some of that manufacturing activity, I know DARPA is they're doing a Proposers Day discussion next week or so on how do you do 3D printing on the lunar surface. So some of these projects and problems are actually getting attention, and they're possibly going to be getting some funding to go figure out. But something that's important to keep in mind as we talk about what is needed across these systems is they need to all work in ways that are highly automated. Some of them will have to be learning by themselves and improving as we go because they won't have the ability to be serviced easily. And we need those systems to be able to not be entirely self-reliant, but have some ability to be repaired even if there is a challenge with regards to getting access to the actual device or actual system. So these are things that are important to keep in mind. And again, they're not elaborated on in the Artemis plan right now, but it's important to kind of think about them as the big picture because this is what will enable that base. So when we think about what's required for a sustained presence, all of those things are important, but perhaps most important is the ability to actually interact with and have humans be able to deal with those systems. And those autonomous systems, again, on a spectrum of autonomy, will have different interfaces to engage with humans. And we aren't really sure exactly how to do this well yet. And I'm going to say that from a point of confidence because when we look at how we've designed technology for human interaction at scale on Earth, we don't have great models for it. So now I'm going to kind of diverge and talk a little bit about some of the challenges we have dealing with engaging technology on a societal level when we design smart cities, and that hopefully will kind of resonate as we talk more about how do we do the solutioning to help with designing a lunar habitat. So it's very important, as I was kind of just saying, we need to build this future moon-based, lunar base as a place for both people and technology to not just coexist, but to augment each other's presence. And so this is a depiction by Skidmore, Owings, and Merrill. They were hired by ESA to come up with an architectural plan for what a lunar habitat can look like, a lunar city. And so people are starting to think about, well, how do we actually design a city that people would live in, and how do we actually integrate technology into that ecosystem? But it isn't, if you read the report, it's very interesting, but the reality behind it is ambiguous. So to give you a quick story, I would like to welcome you to Vestmannaeyjar. Vestmannaeyjar is an island off the coast of Iceland, and it's where my wife grew up. And the reason why I'm showing you a picture of Vestmannaeyjar is because there's about like 1,000 people on this island. It's part of Iceland. It's a very big fishing hub in Iceland. And I was one day we were taking a trip to Cambridge University where I was giving a lecture, and we stopped over in Iceland because they had really good cheap flights there. And so we stopped off in this area where my wife grew up, and we were walking around. My wife says, look over there. That's exactly where the first traffic light was installed when I was 5 years old. And I look at the area, and it was right around where this picture was taken. And I say, okay, well, why is there a traffic light here? And she said, well, actually, that's what all of us were wondering. We have 1,000 people on this island. Most of them are not here all the time. They're not like full-time residents. They're fishermen. So why the heck do we need a traffic light? And traffic lights are like really dumb technology for the most part, but it's technology. And it's one of those things where they wanted to install the technology, the traffic light, for the sake of having technology, for the sake of having a traffic light. And I think they've since taken down the traffic light, even though they are getting a lot of tourism traffic and perhaps they need them more now. But it's an example of how cities are often designed not necessarily for what technology you need, but what's the cool, flashy thing, hot button issue of the day where we think we can have a good fit for technology matching with societal needs. And this was an interesting story because it kind of gave you the flavor of, even in this really remote area where it's snowing, icy cold, and miserable most of the year, where not many people are living, they still really wanted to install this traffic light, even though there's no people there. So sometimes we install technology in cities for technology's sake, not for humans' sake. And so keep that in mind, again, when we're thinking about designing a habitat for the moon. Now, another challenge that we experienced that I'll talk a bit about at Accenture is when we worked with international partners, it was always a bit of a mess. And not just because they're international, but just any collaborators in general. And so when you look at the gateway concept, which is the, I guess, the habitat that will be orbiting the moon or nearby to be able to help with landers that would actually go to the moon itself. When you're looking at that, there's a whole bunch of different partners that will potentially contribute to that gateway. And they're international in nature. They'll be coming from a whole bunch of different manufacturers. They'll be having a whole bunch of different software that's built by a whole bunch of different software companies. And so it'll become this massive system integration mess. And just to tell you a quick story about how sometimes this plans out, not on the lunar surface, but in cities. I was part of this organization called, well, at the time it was called City Digital. Now it's called City Tech Collaborative. It was a public-private partnership that was formed in Chicago out of University of Illinois. And what they were trying to do was design smart cities. And in order to do this, they pulled together a whole bunch of private sector companies, asked the companies to give them some money in order to kind of bootstrap some of the smart city programs. Then they engaged directly with the government of Chicago, the city government of Chicago. And they also started to try and pull in a whole bunch of different public entities and agencies that would possibly benefit from smart city type services. And this organization ultimately was able to fundraise a couple $1 million to start out from these private companies. And we all thought that money would go towards designing the technologies. But then slowly they were asking us all, okay, well, can you go build out the technology and the digital systems for the smart city use cases that we're considering on your own dime? And we wondered, like, what are you using all this money for? And what ended up happening is once we had a solution, one of them was called Digital Underground, where you would actually be able to map out digitally all of the underground assets that are in a city, which is actually a really hard problem to solve. It may sound simple, but it's actually really, really difficult to do. So when we designed this technology to do this platform to enable this, and then also started pulling in all of the blueprints from the city to show where there are cables buried and electricity lines and stuff of that nature, we brought it to the city and said, city, okay, like, let's do this. Let's go adopt this. Let's start using this for, when you have Verizon installing new fiber optics and things of that nature. And they said, okay, well, time to bring in the lawyers. And all the money that was kind of pulled together by this collaborative went to legal fees in order to deal with the system integration and data protection mess that occurred when you have different organizations working together. And so something that we need to be thinking about a bit when we design future cities on the moon or even on Earth here, but when we're designing these problems and we're trying to engage international collaborators, from the start, it helps to have a vision for how that engagement will work. What are the rules of engagement, and how are you going to actually plug in different components from different organizations? What is the data management strategy across these different organizations? Who gets to own the data? Who gets to manage the data? Who gets to manage the technology? Imagine on a lunar base, we're going to have all of this autonomous function that is hopefully going to be designed at some point, but it's not going to all be built by the same manufacturer. It's not going to be built by the same defense contractor or the same government. And so requiring that integration of these components is a necessity, but it's also a really tough challenge from a governance and policy standpoint that I don't think we've even begun thinking about yet. So it's a consideration that we have even in cities here on Earth. And so the last kind of point that I'll make in terms of some challenges that are coming up when you see in cities, but also can be mapped back to the lunar habitat in the future, is assurance is not really straightforward. And I have a picture here of just a clip from the Space Force, which is on Netflix, where there's a image of a Chinese spacecraft that's like clipping the solar panels off of an American spacecraft. And it harkened back to the idea that you're not really sure what's going to happen all the time. And you need a way of kind of thinking about and governing some of these messes, even if you're going to, especially if you're going to send up highly automated systems into an unknown environment. And it kind of speaks to the nature of the Wild West of how we're going to be dealing with this from a policy and governance standpoint and an ecosystem standpoint. How do we actually govern all of these systems acting together, maybe that have different manufacturers or different countries that are behind them, or even how are we going to start thinking about this from a technology integration standpoint or a policy international law standpoint? These are very tough challenges for a lunar habitat, but we don't really have this figured out for the Earth yet either. And so we used to work on a program called Smart Dubai, and a big eye-opening moment for me was when we were kind of helping to design future firefighter capabilities for Dubai, who has historically had a whole bunch of very high buildings that catch on fire because it's really hot and they have other electrical faults and things that happen there. And so they were trying to figure out how do we deal with the security of these buildings from a cyber standpoint, given that they need to provide access to a whole bunch of different organizations to manage the fire alarm system and the building management systems of these massive skyscrapers. And they didn't really have a plan to figure out the security or the privacy around the data of the building occupants, the owners, the ability to actually actuate systems. There was no real governance plan. And so this is something that also is a hot issue right now because Saudi Arabia is standing up a city from scratch called NEOM. It's going to be a $500 billion investment that they're making to build this smart city from the ground up. And one thing that I'm commending them for is that they're working with the World Bank on designing governance structures for the cybersecurity of the smart city. And I think we need to be thinking about this, in tandem with how we design the assurance mechanisms of the autonomous systems that we're going to be putting on the moon. And so these are just kind of, again, some mappings of problems that we've had on Earth and how do they relate back to issues that we're going to have in space. So one of the main advantages, though, as I mentioned very early in the talk, to designing future AI systems and something along the spectrum of autonomy in space is looking at how we are dealing with a greenfield development system here, where we don't actually have to deal with a whole bunch of legacy mess that we already have. And this has been a challenge from a standpoint of cities around the world, where whenever we try and make things smart or try and make things human-centric or try and actually design systems to actually serve society, we're always dealing with existing legacy infrastructure. And that creates a whole bunch of problems from a technology standpoint, from a use case standpoint, from a policy and governance standpoint. And right now we have this unique opportunity to do it possibly right from the start and design technology for human's sake on lunar habitats. And so this notion of having a green space, a green field design for space is really appealing. And so the question that now we would ask is, like, how do you actually begin to build for resilience? And you have to start by enumerating what the needs of a system are. And not just, when I say system, I mean a system that's relating to both the technology's needs. So how do you actually enable resilient technology infrastructure on a greenfield environment? But also, what are the human needs in that greenfield environment? And so some of the research that I've been working on recently is trying to design what we might think of as a hierarchy of needs, relating back to Maslow's needs hierarchy from decades ago at this point, or many years ago. And so how do we actually take this and map it to what are the needs of the autonomous systems and the technology that we're going to be deploying in a space environment? Then how do we actually take that in respect to, well, these are not just needs of technology, but they're needs of technology that have to serve people. And we have to have this technology to serve the astronauts that are there, but also be able to act without the astronauts constantly intervening. And so this is something that we're trying to think about now, because I would say that I don't have this perfectly done yet. And there needs a lot more, we need a lot more collaboration to figure out, like, what are actually the requirements and the needs for these systems. But a lot of that starts with, like, what are the needs of the base? We need to have that written out. We have to have a better understanding of what our goals are for that. And I don't think that's well enumerated yet. And so as we continue thinking about how do we work towards the needs that I may have represented there, something that I'm excited about and research that I'm currently pursuing is, how do you begin stress testing designs for the autonomous systems that we're beginning to build or think about and enumerate. And we have a lot of precedent for the idea of stress testing. We have crash tests, as you see on the slide here, but there's been a whole bunch of work done in the past on V&V for technology systems. And we need to be able to kind of start mapping that onto, well, what makes for a good test to make sure something is actually human-centric? How do we actually be able to design that human-centric component from the start and have that be part of the actual testing framework for these things? And so some of the research that I'm engaging on now is to look at how do we design stress tests for these systems and how do we evaluate the success of stress tests for autonomous systems, looking at space as a use case more than anything else. And so the way we're currently thinking about this a bit is looking at it from the standpoint of having these 3 failure modes and thinking about it from a very kind of historical fault tree aeronautics perspective. And so there may be internal faults of a system, there's external faults of a system, and then there's this other kind of massive failure mode, which is we call ethics, but it's something relating to human centricity of the autonomy of the system. There's some kind of human component that we need to be testing as well. And again, we haven't landed on this yet. So all of your comments that I'm sure are coming in at this point are like, this doesn't sound right, fix it. Well, please help me fix it, because we're still trying to think through how do you actually design a test to make sure something is the appropriate amount of has the appropriate amount of human centricity. And so we're currently designing out frameworks that would help to begin assessing if there are failure modes of the autonomous systems that we'd be deploying in space or in other society critical environments. And so as we think through this, we need to always consider just like the traditional failures, like internal faults, like something just breaking, physical failure mode, maybe a digital fault, digital attack from a cyber standpoint. But then we also have the idea of ethics and how the human component of this is actually critical to the success of the technology itself. And so with that, we need to continue thinking about how do we build this out. And so something that is part of my research agenda kind of has similar points to what you're going to see on the slide here. We need to start first by having better definition of the requirements for what's actually going to be part of the lunar base. Waiting for NASA to kind of help us with that, but it's also up to the community to kind of start thinking about what could be needed there as well. We have to look at that maybe hierarchy that I had proposed for an autonomy's hierarchy of needs and make it less about the autonomous systems needs and more about the human machine teams that would need to be established on lunar surfaces or other, again, societal functions. And we also have to start looking at how do we actually define stress tests that are unique to those needs? How do we define stress tests that are functional in relation to the requirements for the technology that become human-centric? And then finally, how do we refine that stress testing evaluation framework and the criteria that we're going to begin thinking about when it comes to, like, does this stress test, does this tell us anything? Could this system actually work? Is it actually as human-centric as we actually need it to be a resilient system from a societal function standpoint? And so with that, I really would appreciate everyone's feedback and your comments and your collaboration in the future, because these are hard problems that I'm not going to say that I have figured out in any capacity, and that's why I would appreciate everyone's feedback and collaboration. So with that, I'd love to take any questions that are out there. Thanks so much for everyone's time.
Greg, thank you for that uplifting talk as to the challenges that are ahead of us. We really appreciate it. It's going to be great to see some of the research coming out of you and your team out of the OWL lab at IAA when you land here full time later this year. So there's Q&A is open, and we are getting some great questions in there right now. And Greg, I'll go ahead and start from the top and let you comment on them, and we'll go until we don't have any more questions left. There are multiple examples of leapfrogging technologies that had the advantage to start over without old infrastructure norms. So what do you think are the most important examples, like technological or cultural baggage, that a greenfield approach might avoid?
I think the main advantage of a green, and that's a really good question. I don't think I have the perfect answer for it, but I think one of the areas that a greenfield approach helps to avoid is just having a lot of that knowledge of the the previous baggage, and being able to understand what those pitfalls were, and being at a point in time where we do have a fully white space. It's often that when we have greenfield development, that we still have some kind of legacy interference. Maybe a communications channel, or maybe or a protocol, or maybe it's some actual infrastructure. This is a place where we have no comms, we have no material, we have nothing. So we're kind of, I would appreciate that there are other areas where we feel like we have green slate scenarios, but we really are starting from scratch here. And we have a lot of lessons learned. So I think that's probably one of the advantages that this offers us. But I'm not to say that you're incorrect in that there were other opportunities to learn from white space as well.
We may end up with examples of that traffic light in Iceland, where we stick something in and then later on learn that it probably wasn't the best thing to put in there.
Exactly.
Next question. I'm heartened to see the realization that we need to take a more human-centric approach to technology, especially with regard to the development of AI and autonomy, which will require a cultural change for technologists. That human factors engineering has to be not an add-on as we treat it now, but as a foundational consideration for systems engineering and development. Comment?
Yeah, I couldn't agree more. I think it's very heartening, right, to see the human factors from the start. And having designed technology for many years now, I don't think I've ever seen as much of an uplift in the community to support this human centricity of design as I do now. And I think especially as we design AI systems and systems on that spectrum of autonomy, it's going to be more important to have those human factors, given that AI does one thing really well, which is scale. And so after it unleashes on a application space, it scales really fast and really well if you allow it to. And so we have to consider those societal implications. And doing that from the start is the only way of going about it.
Very good. And you talked about human and computer systems that have to operate as teams out there. So that's just another challenge. Next question is, can you summarize one or two key research directions in assured autonomy that have some algorithmic or mathematical challenges? Or perhaps clarify what success looks like for research in this area in terms of quantifiable metrics?
Yes, it's a great question, and I'd appreciate it. Ken, you can take that person's name down and for me and follow up. I can follow up with them, because I think one of the challenges that we're learning about is that we don't really know what the metrics look like right now, and I don't know if we have designed the perfect approaches to come up with those metrics yet. And it would be, I'd be speaking from a point of ignorance to answer that off the cuff. So if I can follow up with you on that, that'd be I'd really appreciate that.
Good. I see in line here, Veronica has offered to connect you with the questioner, so that'll all be taken care of offline, and maybe we'll see it in your future research. Then another question is, what are your lessons from ISS, where maintenance time overwhelms the time to do science?
Yeah, that's exactly that's a big challenge, and it's a resource problem, right? It's a resource trade-off issue that is not always fully acknowledged. The reality is operations and maintenance is always the priority, given you don't want your old systems to die in the process, and I don't think that there's a good medium to. I don't think there's a good answer for that. It'd be ignorant for me to kind of, again, say this is the right equation to balance the two. However, I would say that the research community is very excited about a lot of these future opportunities. If nothing else, in the past 4 years, there's been a huge public excitement about space and space infrastructure and challenge of that matter. And so similar to how I encourage companies to outsource their security research to the security researchers that are out there, I think that there should be improved communications between those who are supposed to be thinking about the future challenges and the future designs. They should communicate those out to the broader public community, because there are many of us who want to talk about these things who may be not paid to deal with it, but we want to actually work on it in a rigorous manner. So that's kind of what I would encourage these agencies to begin using the opportunity that the public really cares. And when I say public, I mean everything from academic researchers to private think tanks and the likes of those.
Okay, good, thanks, great. Next is a longer question. Great talk, Greg. I am an astrophysicist and software developer at APL focused on astronaut health, AI ethics, and data pipelines. A fundamental need of many of these human-centered challenges across applications is a thoughtful, intentional, and explainable design that can adapt as our understanding of the needs changes. What are your thoughts on this? Drawing on your dynamic experience, what are actionable ways that you have seen organizations approach components of this procedurally and culturally? For example, evaluating impacts versus intentions, balancing iterative development versus assurance, etc.
Clearly, you know these problems really well. Whoever asked this, I think, very well framed problem. What I've seen is that a lot of it starts with figuring out how to design an audit log of behavior and activity. And so when we talk about explainability of these systems and also the design of these systems and the intent versus the actual build of the system, we end up breaking down because we don't have a good understanding of how we get from point A to point B oftentimes. And that's because we're just not actually documenting the processes that we're going about or the data that's maybe flowing from the technology that we're designing. And so some of the steps that we've been taking to try and rectify this is by designing embedded in situ monitors for certain technology systems or certain models that would be able to help us understand what this model is doing while it's doing it. And again, we're far from having the right answer, or the perfect answer for this. But I think that developing in situ audit logs of technology systems and understanding where that starting point was, but also where the design intent was coming from, could be a good first step in the very complicated challenge that you raise.
That's right. Good. Thanks. Another one. Can you give some concrete? Hang on a second. Can you give some concrete examples of technology designed for human use versus technology adapted for human use, especially in spaceflight? I like the example of the traffic light, but I'm curious what issues specifically have come up for Artemis.
So really good question. I'm going to be telling you that I actually don't have any insight into Artemis beyond what I've been able to read from the public documents that NASA's released. I'm not part of the Artemis team or any teams that are working explicitly on lunar habitation. So I don't have that insight. I'd love to be able to learn more about that. And I've reached out to a number of colleagues at APL to see if they can share information. But I think that generally a lot of this is under tight wraps. Again, kind of harkening back to my call for, like, let the public know about some of this information, even if you're still in the brainstorming phases of it, because we want to help. We want to be thinking about these challenges and relating our own experiences to them. So I'm sorry I can't answer your question better than that, but I'd be just making stuff up if I were to give you examples.
Well, making stuff up from your experience might also be informative, but I understand what you're saying about things being under wraps. It would be good if we could identify those traffic lights out there and get more discussion around them, maybe make them a little more transparent. Let me continue with the questions. Many of these issues have been understood for some time. For example, city design, grid layout, and thought out planning, for example, versus just growing from the beginning. Given that we understand that these are issues, how do we get the funders to fund the issues?
Yeah. Well, I think it's different when you talk about it from a city standpoint and then also from a space standpoint. the reason why it's challenging from a city standpoint to design around the issues and to fund around the issues is that the issues are not sexy, and they're often kind of relegated to the bureaucratic lawyer type folks to try and deal with, but then it gets buried under paperwork and legal fees that aren't able to be figured out. Even the technology design challenges end up becoming matters of legal challenge. So for example, I remember designing a system. It was also with that consortium in Chicago. My team was designing a system that had to integrate with something that Siemens also designed. And we were trying to solve a very specific technology challenge, but it ended up becoming a mess because of the IP arrangements of that. And so even though the human-centric will was there from the funders to actually design the right technology, there wasn't a good legal framework for us to operate under that would actually allow us to work through some of those challenges easily. Yeah. And so I would say that, you know, sometimes those areas are funded, but then it gets played out in litigation, and then everything disappears everything, all the money disappears. From space, I think the slightly different perspective, because we have more government agencies involved, which may make it harder, but also means that maybe they'll be willing to spend money on these questions of policy and things that are maybe more of the fundamental guts of the system, the kind of like squishy white underbelly questions that we need to deal with that companies don't like to pay for, or funders don't like to pay for, or VC don't pay for because it's not sexy. But I think government agencies are a little bit better at funding some of those sometimes. So maybe I have a bit more hope there. But again, it's not a straightforward question and solution set, given funding is always issues for these human-centric design challenges.
Indeed. I'd also like to invite my fellow panelists who may have burning questions they'd like to ask to just jump in and interrupt me. We've still got some questions on the Q&A list, but panelists, please feel free to jump in here if you have a question to ask.
Ken, this is Tony. I'd like to jump in with a question for Greg. When you talk about these complex and largely autonomous systems, Greg, I'm not too worried about component failures. I think, you know, with a lot of engineering, we can handle those kinds of things. I'm always reminded of the book by Charles Perrow called Normal Accidents from the 80s, and I think there were several other editions of it, in which I think the takeaway is that when you have these complex interacting systems, there are situations where each component of the system is doing what it's supposed to do, but then the overall system gets into a situation where the overall system does something that you really don't want it to do. And he cites instances from Chernobyl, airline disasters, tankers colliding in the middle of a body of water, and so forth. And that's what really worries me about, you know, when we talk about these systems. Can you comment on that, please?
So I'll throw some of your own material back at you, Tony. In terms of IAA has 3 pillars, right? We have technology, we have governance and policy, and we have ecosystem. And the challenges that are probably defined by the book you described are largely relating to technology themselves and how those technology systems are interacting is where they break down. And so that's where the question of how the ecosystem helps to manage all of the components of the autonomous system or systems that are interacting. And we need better understanding of how we can design ecosystems to have active roles in the agents that are part of an autonomous system ecosystem. And so that's where smart cities becomes a very interesting challenge to think about, because it's really not always about the technology in the city. It's about the governance and the management of those technologies and making sure they're orchestrating and interacting and engaging correctly. And also making sure that the outcome is, 1 + 1 = 2, not 1 + 1 = 3. And so I think there's a very big role for the ecosystem to play to manage failures, maybe failures that are, things where things are meeting design intent, but they're not interacting as they're supposed to, or even if they're interacting as they're supposed to, there's maybe some error. And that's where the ecosystem needs to be able to have a more active role in managing that failure. And again, I think smart cities as a concept is a good place to think about it from a platform standpoint, where you have a whole bunch of different technologies that maybe live on a unified platform or city operating system, as we used to define it, that actually has an active role in engaging these individual technology systems. And I would expect that, for actual cities or for things like the lunar base, we would have that underlying platform that would serve as that ecosystem to manage the interconnected failures that may occur. I hope that answers your question, but I think that's the challenge is really in that ecosystem.
Thank you. Yeah, I think it's a huge challenge. Thank you.
So Greg, this is Ashutosh. I have a small question. I know you briefly talked about security aspects. What parts of security you are really worried about? Is it the networking, communication, interdependency?
I'm actually personally most worried about the edge.
Okay.
And I think that the reason why is because it takes time, but we get pretty good sometimes at designing networks for security or designing networks for failure. But we're really not really good at designing endpoint security right now, especially for constrained devices, and especially for space systems. We're going to be dealing with a lot of constrained devices that are essentially IoT devices in space. And so I think that that's where I have a big concern, and also having done a bunch of security work for space systems, specifically on CubeSats, that's where we're seeing a lot of challenges. It's not necessarily in the comms protocol. It's not even on the ground station. It's in the control system on the edge. So I think that's kind of where the challenges are going to be in the future.
Thank you.
Thanks, Ashutosh.
Quick question that we got in the chat. Tony, there was a question about what the book was that you referenced. Could you send it to all? Oh, you just did. Never mind.
Yep.
Thanks, Tony. Let's see, Greg, next question. Will we truly have a green field for efforts like Artemis? It seems like the grip of existing systems and contractors is pretty strong. The Space Launch System is one example. Not right for the job, but congressional favorite. So any thoughts on that?
It's a good point. We do have to live with the existing and political biases that we have towards certain programs and technology. But that's where the role of the researchers and the designers should come in terms of helping to think about what is the art of the possible before we actually start commissioning these systems. And I think the time is now to actually be envisioning that, because if we can't provide a cool vision and how it should be from that greenfield standpoint, as a true north, as we call it in strategy consulting, we're going to just be reliant on the SLS and things of that nature, because no one really can envision anything better. Again, calling for transparency and communications across what we actually can imagine versus what we have today.
Yep, sharing is key. Got time for probably one more question here. You mentioned that your work involves exploring a variety of frameworks for stress testing. Where do these frameworks originate? Are they adapted from specific organizations or domains, created by your team, both?
So I don't think there's value in designing frameworks from scratch. And so what we've been doing is taking a pretty multidisciplinary approach to creating these stress testing frameworks, looking at fields as far flung in this world as looking at biology and looking at faults in genes, as well as looking at more traditional aeronautics fault trees or attack trees, or even formal methods that have been employed for the past several decades. So there's a whole bunch of different V&V, verification, validation, testing mechanisms that have been kind of proposed over the years. And I think my team and I don't believe that any of them are perfectly a fit, which is why we're trying to take a little bit from each and seeing what magic we can make. Great.
I'll leave it on that. We're certainly looking forward to magic and in your research and in your working with the rest of the folks on this talk. Thank you so much for your thoughts today. It was a wonderful seminar. It gets everybody thinking about where things can go. Everybody, thank you for joining this talk. We look forward to seeing you next month. Goodbye.